Hello everyone, welcome to ECE 161. So my name is Tolentino. I'm your instructor for today, and we're going to discuss Lecture 9, Discrete Fourier Transform. Okay, so this will be the outline of our lecture for today. Okay, first of all, we want to introduce the discrete Fourier transform, some motivation behind the operation. Why do we need this kind of transform instead of just the discrete time Fourier transform? Number two is we define the formula or the computation of this kind of transform. And number three, we solve some examples using the direct computation. And number four, which we will be discussing on the next part of this video, will be the properties associated with this transform. Okay. So first, for our introduction, some motivation behind this transform. So why do we need the DFT? Okay, so why not just use the discrete time Fourier transform? Because basically um, what we want to do here is to represent the time domain signal into its frequency domain. So, and we've already done that. Basically, time domain signal is in general discrete time and aperiodic, right? So, all signals or most of our signals, practical signals, exhibit this property in the digital domain, right? So, if we want to represent that in the frequency domain, we use the discrete time Fourier transform, right? Because that time domain signal is discrete time and aperiodic. So we use, if you could recall, our formula for that is, this is x of omega summation from n is negative infinity to infinity, our time domain signal, which is aperiodic, e to the minus j omega n. This is our DTFT. Okay. So the problem with DTFT is that our frequency domain is represented as a continuous function. So as such, so this is our example. Suppose that x of n is this exponentially decaying function. Okay. For example, this is our x of n. And again, this is discrete time and aperiodic. If we want to get the frequency domain, we have this function, which is in general a continuous spectrum or a continuous function. The problem with a continuous function is that we cannot represent it in the digital domain because we have infinite amount of information, right? So that is the motivation behind the discrete Fourier transform. Is it possible to somehow represent this kind of function in the digital domain? So the most obvious or simple way to do that is to discretize the frequency domain. So is it possible that instead of getting this whole spectrum, we sample? Okay, so we sample only specific points, okay, in this frequency domain representation. So when we do that, okay, some review on sampling. If we want to sample something, we multiply it by this function, the impulse train, right? So for example, we want to sample the frequency domain by this formula, 2 pi k over n. Basically, if you could recall, right, our range of values for the DTFT is from 0 to 2 pi, right? Omega is from 0 to 2 pi. And if you want to sample n equally spaced frequency point, we use this operation. Omega sub k is 2 pi k over capital N, where k now is an integer. Basically, it just implies that we are now in the discrete frequency. Okay. So multiplication, this continuous function multiplied by this impulse train will yield us a discrete frequency. Now, okay, for example, this is our, what do you call this? For example, this one is x1 of omega. This one is x2 omega. Now this is equal to x3 of omega, right? What is the, what is, what do you call this? What is x3 of omega in the time domain? So we know x1 of omega in time domain, right? That is just this one, x1 of n, right? We know x2 of omega in the time domain. If you could recall, the impulse train is basically a good, what do you call this? A good signal, because an impulse train in the time domain is also an impulse train in the frequency domain. So x2 of n is just also an impulse train. Now, if we multiply in the frequency domain, recall that property. If we have multiplication in, or or for example, multiplication in f, what we are doing right now is multiplication in f. That translates to convolution in time, right? And on the other hand, convolution in f is multiplication in time. Okay, so we utilize that property. So in this case, if we have multiplication in frequency, we are convolving in the time domain. So this one is x1 of n, we already know it. This one is x2 of n, the inverse Fourier transform of x2 of omega. What we want to get is what is the time domain representation of x3. It is equal to this one. So what happens when we convolve something with an impulse train? We are just generating replicas at those impulses. So basically, convolving this one to this one will yield us these replicas to this type impulse positions, right? So yielding us this function. This is our x3 of n. Now the takeaway here is that we can make x of omega discrete, which is our motivation for DFT, by making our aperiodic sequence periodic. So if you could recall, right, if we have a discrete time and a periodic signal, it is equivalent to discrete in frequency and also a periodic in frequency. So what we've done is, since we've discretized in the frequency domain, we are now making our time domain periodic. Okay, so that's the key idea here. We can make x omega discrete by making our time domain signal periodic. Now we formally defined the discrete Fourier transform. So what we've did so far is, this is our, what do you call this? The DTFT. Okay, this is our DTFT. So from the DTFT equation, we sample x of omega at omega k is equal to 2 pi k over capital N, because we are sampling n equally spaced frequency points. Okay, so if our range of frequencies in DTFT is from 0 to 2 pi, then we are taking 2 pi over capital N number of points, where k here now is an integer. Okay, if we do that, substitute this to this one, this omega here, we now have this formula. This is now our DFT expression. Okay, so in formula, this is our equation, and the inverse of that, inverse DFT, it's also taken from our inverse DTFT, right? The only difference is that we are scaling it by the period n, and instead of a negative exponential, we have a positive here. Okay, so So that's it for our DFT. Now, let me have this example. For example, we have x of n. Now take note of L here. L is the length of x of n, right? So if we have a certain time domain signal, okay, with length L, and then we represent it in the frequency domain by DTFT. So from the DTFT, okay, since we have a continuous spectrum, how many points should we take from the DTFT representation? So in this case, for example, this continuous spectrum, okay, how many points will we take from that so we do not lose any time domain information? So consider this one, 0 to L. If we choose n, for example, n less than L. Okay, if we choose n less than L, if you could recall, right, n is the period wherein we convolve. For example, we said n is 50, therefore we are convolving with impulse train spaced by 50 samples apart. So if we take n less than L, what do you think will happen? For example, this is our n. Okay? This is our n. So we are taking replicas of this and then generating it at this point. Therefore, we are basically losing this information, right? This information is part of our x of n. So if we have n less than L, we lose information from our original time domain signal. We do not want that, right? Okay, from xn. We do not want that because we want to represent x of n in the frequency domain without losing the original representation. So in general, we should choose n less than L. Okay. What if n is equal to L? So n is equal to L. It's technically all right if we choose, for example, in this case, right? For example, L is 50. L is 50. We have chosen actually n is equal to 50. Okay, 50 samples. That is all right because we can still take the inverse transform of the DFT and still arrive at this time domain representation because we are not losing any information there because we are taking period at exactly the length of L. But the implication of that is that we have a poor picture of the frequency domain, which we will discuss later. Okay. So now, the DFT provides the relationship between the periodic and discrete frequency spectrum and the discrete. So basically, x sub p of n is the inverse DFT of x of k. So, and in general, it is equal to the original time domain function, and we sum all of the shifted versions of that time domain. So, for example, in this case, right, if this is our original x of n, we shift this x of n by the period. So, for example, this one, and then we will arrive at x sub p, right? So x sub p. So that is now that x sub p is the inverse discrete Fourier transform of xk. Okay, when n is greater than L, okay, we are not losing any information, right? So x of n is technically equal to the inverse DFT of x of k at this sample points. Okay, so this is the goal when we want to take frequency points that are greater than the length of the signal. So as we are representing the same time domain information. Okay, so let us have an example of DFT. So for example, we have x of n is equal to 1. So we have a flat spectrum. We actually have a rectangular pulse in this case from 0 to L minus 1. So for example, L is 10. We have 10 samples of x and then 0 elsewhere. So we have a rectangular pulse. Okay. So the first step is to solve x of omega in the continuous spectrum. Use the DTFT. So to do that, we recall the formula is summation from n is negative infinity xn e to the minus j omega n. But in this case, we only sum from 0 to 9. Right? X of n is equal to 1 e to the minus j omega n. Okay, so recall the property from our discrete math. N is 0 to, for example, n is 0 to k of a to the n, where absolute value of a is less than 1. This is equal to 1 minus a to the k plus 1 over 1 minus a, right? So in this case, this is equal to 1 minus e to the minus j omega 10 over 1 minus e to the minus j omega, which is equal to this one. So in general, L is 10, so we choose this. And if we are to plot that in the frequency domain, we have a continuous spectrum. So this resembles a sinc function, right? So the sinc function. Now from this spectrum, how many points should we obtain from this continuous spectrum? Or in this case, what is n? What should be our choice of n? The number of samples to take from the continuous spectrum. So if we choose n is equal to 10, that's step 2. Determine the samples of x of omega. Okay. So in that case, we just substitute omega is 2 pi k over capital N to this omega, where k now here is from 0 to n minus 1. Okay? Suppose that n is exactly the length of the signal L. So we get x of k is equal to 1 minus, I'll write it here. If n is equal to L, we have x of k is equal to 1 minus e to the minus j 2 pi k 10 over 10. So this is it. Divided by 1 minus e to the minus j 2 pi k over 10. Now this one is 1 minus is this right? Okay, so if we choose k is equal to 0, okay, k is equal to 0, so x of 0 is equal to 1 minus 1, right? Over 1 minus 1. You do L'Hopital's, you should arrive at this value. L, x of 0 is equal to L. Okay? Is that correct? Okay, I hope I'm doing this right. But anyway, if we set x at some number not equal to 0, we are getting 0. So the problem is we have x of k as this one. So this is L and then 0 elsewhere. So it doesn't really capture this one. Okay, that is all right because we are not losing information here, right? Or let me just for example, this one is our, so for example, this is 10, right? And then if we choose n is equal to 10, then we are generating replicas of this impulse train at 10 samples. So technically we will have, so this is our point of periodicity, right? So technically we will get a line or a constant, which does not really um, say that this is actually a rectangular pulse. You just say that it's a rectangular or a constant. That's why we are getting this one. That's why we are getting this impulse only. Okay? Is that right? This is still correct in the sense that um, x of n is equal to x sub p of n for 0 to n minus 1, right? We are not losing information, but if we want to know that it's actually a sinc function, we should choose n greater than L. So for example, if we choose n is equal to 50, so n is equal to 50 will generate this is x sub p, right? And this one is this. So for example, this one is the continuous, right? So we get 50 samples from that, generating as this function. So if you count the number of samples here, 1, 2, 3, 4, 5, 6, 7, you should count 50. So that is now the shape of our spectrum. Now, for example, a while ago we choose n is 10. N is 10 samples. So from the continuous spectrum, we choose 10 samples. So you should notice that we choose, for example, this one, we choose this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see you see where this is going. We are getting exactly at those zeros. This is not entirely aliasing, but it's something like that. Aliasing, right? You are not getting the true picture. So in general, we should choose actually n greater than L. So the trade-off here is that we take more samples, so you should have more resources for that. But the good thing here is that we are now getting the original continuous spectrum better, right? This is a sig function. So in general, we should choose n greater than L for a better frequency resolution or better picture of the frequency domain. If n is equal to L, x of n is equal to x sub p, we capture the information of the original time domain signal, which is okay, but a poor picture of the frequency domain. So some comments about n greater than L. What we are actually doing is we are appending zeros, or what we call this zero padding, right? So some caveat here is that zero padding, it does not provide additional information about x omega or x of n because we just add zeros, but it actually improves the frequency, the picture of the frequency spectrum. Okay. So for summary, summary so far. We're not done with this lecture. Basically, if we want to get the DFT of an aperiodic sequence with length L, we can obtain it by sampling the continuous spectrum at n equally spaced frequency points. Okay, when we do that, we are making the original time domain sequence periodic with the same period, capital N. So the period of in the so it's an important thing to note here that if we take n samples from the frequency domain, the period there is n, right? So x of k, the period is n. That same period is also the period in the time domain. Okay? And we choose n not less equal to L but greater than L to provide a better picture of the frequency spectrum. So that ends our lecture, part 1 of our lecture 9. So in the next part, we will discuss some properties of the discrete Fourier transform. So see you there.